Hi viewers, welcome to our electrical engineering lectures channel for most interactive sessions of different subjects of electronic and electrical engineering. For the latest updates and videos, don't forget to subscribe and click the like button.
Assalamu alaikum everyone. In this lecture we will be discussing the phenomena of intersymbol interference in digital communication systems. So intersymbol interference is basically a phenomena which is caused due to the band limited nature of the wireless channel, which forces the transmitted pulses to smear and interfere with the adjacent pulses. To have a further understanding, let us take a very simple example that if we are going to transmit, let's say, these 3 bits and the NRZL scheme from +1 to -1 volts. If we draw the NRZ waveform, it will be like this. For 1 it is +1 volt, for 0 it is -1, and for 1 it is again +1. And the x-axis is representing time. This is 1 symbol period, this is 2 symbol period, and this is 3 symbol period. So these kind of rectangular pulses are not physically realizable to transmit. If you transmit such kind of rectangular pulses, because the channel is band limited, so what the channel does with these pulses is that the pulses now become like this. For 1 it can be like this, for -1 it may be like this. So the portion here, this portion, you can see here both the pulses are smearing into each other. So this smearing causes interference, and this interference will result in the distortion during the detection process. So overall, this phenomena is called intersymbol interference. So to have a further detail, let's have first of all let's have a look at the overall receiver structure that we have already discussed in the previous lectures. And we see that where is the point at which we need to insert an equalizing filter which will be responsible for the mitigation and reduction of intersymbol interference. So if you see this diagram, the received signal is R of t. It first of all passes through the frequency down conversion to convert the band pass signal into baseband signal, and after the baseband signal is formulated, it will pass through the receiving filter. Receiving filter is the matched filter, which is already covered in the previous lectures. After passing through the matched filter, the next stage is equalizing filter. So this equalizing filter is responsible for the mitigation or reduction in intersymbol interference. We need to design such a filter which will try to reduce the intersymbol interference as much as possible. So if we see the overall baseband system model from end to end, let's say we are going to transmit, as an example, 3 symbols which are x1, x2 and x3. x1 and x2, they are on the positive side, and x3 is on the negative side. This is the symbol duration, which is capital T. So if you see from end to end, from the transmitted xk to xk hat, which is the detection, which is the output of the detection. So for the complete end-to-end system, we encounter 3 kinds of filters. The first filter is transmit filter, whose impulse response is ht, and the corresponding transfer function is capital HT. The second one is channel, because wireless channel can be modeled as an LTI system in most of the cases. So the channel impulse response is hc of t. And after the addition of noise, the third kind of filter, which is on the receiver side, is receiver filter. So you can say that the transmitted sequence xk, it undergoes 3 different kinds of filter: transmit filter, channel, and then receive filter. So as all 3 filters come in cascade, if you see from end to end, so you can say that the overall transfer function h of f, it will be given by this particular equation, which is basically the product of the transfer functions of all the 3 filters: ht of f for the transmit, transmit filter, HC of f for the channel, and HR of f, which is for the receiver filter. So as a product of these three transfer functions, you will get the overall transfer function. And the purpose of the complete overall transfer function will be to mitigate the effect of intersymbol interference by designing carefully the filters HT and HR, because the channel transfer function is not in our control. The maximum we can do is to design the transmit filter and the receive filter so that to mitigate the effect of intersymbol interference. So now let's further look into this diagram. Again, come towards the sequence xk. We are going to transmit x1, x2 and x3 after passing through the transmit filter having any arbitrary impulse response. The output of this filter may be like this. If it has a triangular type of impulse response, then these are x1, x2 and x3. When it passes through the channel, it becomes channel, and after the addition of noise, and then it will pass through the receiver filter. So if we formulate the overall equivalent model by combining all the three types of filters into an equivalent system H of f, what will happen? If you see the second diagram, again we transmit x1, x2 and x3. After passing through this equivalent system, the output at this point is the same as this one. So these two are similar except the noise. We have just taken the noise aside, and these three filters in cascade. So the output z of k at this point will be the same as the output z of t at this point before sampling. So now if you see, let me draw the same concept over here, that you have a sequence xk shown by this typical 3 sample signal. This is x3 and the duration, simple duration is capital T. So if it is passed through an equivalent system, having transfer function of h of f, what will be the output? The output will be like this. Corresponding to the first sample x1, we may receive a signal like this because of the band limited nature. For x2, we can have another pulse like this, and for x3 we can have similar pulse in the opposite direction, right? So where this duration, again this is capital T. Now on the receiver side, this particular signal will be passed through the sampling stage, and the purpose of sampling stage is to sample after every symbol period. So let's say we start the sampling process at this point in time. This is the first sample, and equally spaced another sample. So this duration is again capital T, and again equally spaced capital T. So you will be only getting these 3 samples at these 3 points. This one, this is the first, this is the second, and this is the third. Now if you see the first sampling instant, if you sample at this point, it is very much clear that there is no interference from any other pulse, and this is due to the reason that we have considered 0 previous pulse. Now come to the second point in time. If you sample at this point, you can see that this sample will contain portion from the red one and also from the black one, this one. So this red one is the desired. You can say that this is the desired, but this black one is the undesired. These two are added up, and if you sample at this point, the previous pulse is smeared into the current red pulse, due to which it causes interference. Similar phenomena can be observed at the third sampling instant. If you sample at this point in time, here, if you sample here, it will contain the contribution from the red one and from the black one also. So this is the phenomena called intersymbol interference. which causes smearing and thus producing interference due to the adjacent pulses. So now the purpose of the filter design, the receive filter design, is to design such a filter which can mitigate intersymbol interference, which should a pulse like this which can mitigate intersymbol interference at least at the sampling instance, because we are not concerned what is happening at the other times. We are only concerned what is happening at the sampling instant. So if we design a filter which at least mitigates intersymbol interference at the sampling instance, then our problem may be resolved. And the resolution of this problem was proposed by Nyquist. So Nyquist bandwidth constraint, first of all let us discuss this point, and from this point we will see that how the Nyquist filter will be used to mitigate the intersymbol interference. If we use Nyquist filter on the transmitter and receiver side, ISI will be mitigated. So Nyquist, first of all let us see what is Nyquist bandwidth constraint. The constraint says that the theoretical minimum required system bandwidth to detect RS symbols per second without ISI is RS by 2. What does it mean? It means that if we desire to transmit RS symbols per second without ISI, the minimum bandwidth which we will require is RS by 2. If we use bandwidth less than RS by 2, it is not ensured that there will be no ISI. To ensure that there is no ISI, at least we need to have the bandwidth equal to RS by 2. So in other words, we can say that if we have a filter like this, which has the bandwidth of 1 over 2t, the one-sided bandwidth, this is the one-sided bandwidth, 1 over 2t. So if the filter has one-sided bandwidth of 1 over 2t, and let's come over here to have further detail. Let me draw the filter over here. It is a rectangular filter having the bandwidth of 1 over 2t. So W is equal to 1 over 2t, and this is equal to RS by 2. It means if the system bandwidth is this one, we can support RS symbols per second without ISI, right? So in other words, we can also say that the W, the system bandwidth, must be greater than or equal to RS by 2. Again, let's come over here. So the same thing can be mathematically written as the minimum required bandwidth will be W, which must be greater than or equal to RS by 2. And this inequality can also be written as RS divided by W is less than or equal to 2. Now, what is the unit of RS? It is symbols per second. And what is the unit of bandwidth? It is hertz. So you can say that symbols per second per hertz will be less than or equal to 2. So Nyquist bandwidth constraint says that in order to have 0 ISI, at least theoretically, the symbols per second per hertz must be less than or equal to 2. The upper bound is 2. You cannot achieve symbols per second per hertz greater than 2. And this particular thing, which is symbols per second per hertz, is denoted as the bandwidth efficiency. I will tell you how it is bandwidth efficiency. Bandwidth efficiency means that it is measuring the capability of any scheme, that how much data rate it can support in a given bandwidth. So if you see the units, let me explain how. The first part, which is symbols per second, what is this? This is data rate. You can also convert it into bits per second. They are very much similar in most of the cases. And this one is bandwidth. So what you are actually finding? You are actually finding that how much data rate can we support per unit bandwidth. So bandwidth efficiency is quantitatively described as the data rate per unit bandwidth. So whenever you encounter such units, bits per second per hertz or symbols per second per hertz, they are corresponding to the bandwidth efficiency. So Nyquist bandwidth constraint says that the maximum bandwidth efficiency of any system with 0 ISI can be equal to 2. It can be less than 2, but it cannot be greater than 2. So that were some words about the bandwidth efficiency. And now we see that if we choose such filters having bandwidth of 1/2t and it is a rectangular filter, so if we are interested in finding out the impulse response of this filter, so if any system, any LTI system has a rectangular frequency response, then it is understood through Fourier transform pairs that the impulse response of this filter will be in the form of a sink, and that is denoted over here. Corresponding to this h of f, the impulse response is sink of t over capital T. And if you find zero crossings of this sink function, so you must know that zero crossings will be equal to the argument of the sink function, and you just make it equal to plus minus n, where n is from 0, 1, 2 to infinity. So it means t will be equal to plus minus nt. So it simply states that the zero crossings will occur at the integral multiples of the sampling period. Now if you draw the sink, you can easily see that this sink has the first zero crossing at capital T, the second zero crossing at 2t, and so on. Similarly on the other side, minus t, minus 2t, minus 3t, and so on up to minus infinity. So it is a sink which has the zero crossings at the integral multiples of capital T. Now how this filter will be used to mitigate ISI? This is the main problem. Now come again to the diagram, the end-to-end diagram, which we were having which we were discussing a bit earlier. If you see the second diagram, the equivalent model, I have already explained in the notes. And now just assume that instead of using this arbitrary pulses, we now use Nyquist pulse, which is in the form of sink. Now what will happen is, will there be ISI or not? So just again we draw the same diagram, assuming the use of Nyquist pulse instead of the arbitrary pulse shape. The same data will be transmitted through the equivalent system, which is h of f. Now assuming that this equivalent system, this equivalent h of f is the Nyquist filter. If this is the Nyquist filter, what will be the output? Now carefully let us draw the same thing over here. Corresponding to the first sample x1, we will have a sink with positive amplitude. So let me draw such kind of sink over here. So this is corresponding to x1. Now we say for x2. For x2, it will be spaced by capital T. So it means if the zero crossing of this particular x1 was at 0, the peak at 0, then the peak of the second sink corresponding to x2 will lie at capital T. This is capital T, this is 2t, this is 3t, and so on. So the peak of the second sink will be at capital T, and it will have zero crossing at 2t, 3t, and so on. Similarly on the other side, it will be like this, and it will also have positive amplitude because x2 was positive. Now for x3 will be spaced again by capital T, so the peak of x3 will occur at 2t, and with a negative amplitude because x3 was negative, and the zero crossing of this, the first zero crossing will occur at here and like this. and the other side zero crossing will be here, and it will traverse the red one. So this corresponding to x3. So I can write here again mathematically as x1 will be equal to h of t, x2 will be corresponding to the h of t minus capital T, and x3 will result in h of t minus 2t with negative sign. So these three we have plotted over here. Now if you see the same concept, now let me sample it at the sampling instance. So if I say that I am going to sample at the integral multiples of the sampling period, let's say first sample I take from this point. Let me use a different color just to have a more clear representation. Let us choose this green one. So first sample I am taken at here, the second sample at capital T, third sample at 2t. So this is 0, this is t, this is 2t. Now if you see one by one all these three samples, when I sample at t is equal to 0, I am only getting the contribution from the black one. When I am sampling at capital T, I am only getting the contribution from the red one, which is the desired pulse. When I am sampling at 2t, I am only getting the contribution from this blue one, which is the third pulse, which is the desired one. And at the same time, at 0, capital T and 2t, the contribution of other pulses will be exactly 0 because it is passing through the zero crossings. Like you see at this point, let me highlight it. At this point, if you see, I am only getting the contribution from x1. The red one and the blue one are 0. Similarly for the other points. So it means if we use Nyquist pulse for the overall transfer function, I mean on the transmitter side and on the receiver side, ISI will be mitigated at least at the sampling instance. So that is the advantage of using Nyquist filter for pulse shape